All right, here's a quick example of how you can, one method, there's different methods, but here's one method about how you can find the moment of inertia for a thin disk about an axis O through its center. So this would be spinning like a pulley, right? When we did Atwood's machine earlier in the year, we said the pulleys were, and they were, comparatively massless compared to the masses we were using. So we ignored the idea that the pulley could have rotational inertia, and when we did the Atwood's problems, we didn't think about that at all. So we're ready now for the next level of complexity where you have a pulley of maybe significant mass. And in that case, in order to get the pulley to rotate, you're going to need a definite net torque. So a pull on one side and a pull on the other side will have to be different so that you can get the pulley rotating. Or maybe it's like a bucket wrapped around the pulley and the bucket's falling and getting the thing to go and different things like that. So you need the moment of inertia of the pulley or the disc. Okay, well you can look this one up in the table, but it's nice to see how this one is developed. And so once again, just like on the rod or the stick, you're going to have some element of the moment of inertia due to some dm. Now the dm in this case is going to be this ring right here. Okay, so some element of width. This is some little element of mass of this entire disk. So by symmetry, we'll choose kind of like the hoop like this. All right, and it's di, right, for that hoop. We have already seen it would be its dm r squared, because all that mass is at the same distance r distributed about O. And so we can use this expression to sum up our integration. Now one thing that's a little bit different here is we defined a thin rod as a one-dimensional object. So when we're going to do a thin disk, it's a thin two-dimensional object. So instead of having our density of our object defined in one dimension, we can define, and I know this is a little different, a two-dimensional mass density. And usually a lot of books will use the symbol sigma for that. So instead of a mass per unit length, or in 3 dimensions where we do mass per unit volume, which is what you're most used to, we can define sigma as mass per unit area. So for instance, let's say you had a piece of paper and you wanted to know its density. You could take the piece of paper, set it on a balance, you'd get its mass, and if you divide it by the area of the paper in square centimeters, you would have kilograms per meters squared. Now, any little piece of that paper that you cut off, if you know its area, you could quickly calculate its mass by multiplying the area of the paper by sigma, and you could estimate what its mass is, as long as the two-dimensional object is a uniform mass density. All right, and paper would be a pretty good idea of what something like that would be. All right, or balsa wood or something like that. So thin sheet of balsa wood. So in this case, with the sigma defined, remember that the area of the entire disk is going to be pi r squared. So our sigma can be expressed as mass over pi r squared, since the area is pi r squared. And again, we're doing this because we need the mass in terms of our variable, right? Our variable that we could integrate over the shape. So what we can do is, if we solve, right, here for m, and we do dm dr, we can see that our dm would be the dA, or since the sigma is a constant, we're going to have 2 pi r dr. So when you take pi r squared and do dA dr, you'll get 2 pi r dr. So what we're going to do is we can take our dm then, which is our sigma dA, right, our little element of area right here that we're thinking about, and when we do the dA dr, we get the 2 pi r dr for the dA. Okay, well, this becomes what we can substitute in for dm now in our integral. So working down to how we're going to integrate over this shape, the whole inertia for all of those ith masses, or those dm's, whoops, there we go. Okay, so what we have is r squared dm. We substitute 2 pi r dr right here, sigma 2 pi r dr in for our dm. And what we end up having to integrate from 0 to r, right, 0 to the entire radius of the disk, we can take the 2 pi sigma out, and it's going to be the integral from 0 to the total radius of the disk of r cubed dr. Okay, well, in that case, we kind of know how to integrate r cubed dr. That's not too bad, right? It's a polynomial. So that's r to the 4th over 4. This is stuff you would have learned right away in your first semester calc class. So from r to 0, we can evaluate that as it's just going to be r to the 4th over 4. And that doesn't look like our moments of inertia terms in our table yet, but remember that we've defined the sigma. And so we have to replace the mass density with our sigma expression of the mass of the disk over pi r squared. So when we do that and replace the sigma with m over pi r squared, then we can see that the pi's will cancel out. On r squared, we'll cancel one of these r squareds, and we'll have 2 over 4, which is a half. So that comes up with our expression for the moment of inertia of a disk. Thin disk spun through an axis through its midpoint, through its center, okay, as you're looking at it. So again, this takes the I for a shape as a constant times mr squared, where k is the constant that depends on the shape of the object and the axis of rotation that you're spinning it through. Okay, so I'm going to load a couple other of these that show you, if you're interested, you probably won't need to know them for the exam, on how you do the volume or how you do the moment of inertia for a three-dimensional object like a sphere or something like that. But if you understand these two, you kind of get the basic idea of what's going on.